Hello, Mike here. My topic today is all about the nuances of reporting and understanding and analyzing water quality data that's in the form of time series. These are my credentials that you see on the screen there. Now, this really applies to quantifying anything, really. How much, how strong, how long, and how often. So the amount of something, the intensity, the duration, and the frequency. So how much? The amount of a pollutant over a specified period, the intensity or magnitude of something. So in this case, pollutant concentrations. How long would be the counting the number of hours that that a threshold is exceeded, and then finally how often. So frequency or return period of an occurrence. And so we have different analyses for these different topics here. And I'm going to focus on the duration, the third bullet there, the duration analysis. So time series are sequential ordered data. It's ordered, of course, with a time stamp. And you need to know, are these measurements at an instant in time, or are they averaged? And over what averaging period are these either measurements or output from a dynamic model like Icwmm? There's challenges and there's decisions that you have to make. How do you handle missing data? How do you exclude zeros or negative values? Do you filter out values that are above or below thresholds? Things like that. And then daylight savings time. I wish we can get rid of it. It would make things easier, at least analyzing time series data. So when you're parsing the data, which is, taking that time series and then splitting it up into pieces, I like to think of it in terms of event-based data, which is to say you're only interested in the events. You can ignore everything that's not happening during events. So the non-events you can ignore, like rain events, flood events, and things like that. And then the other one that I like to consider is what I call period-based events. So you want all the data, but you can split it up into periods, water year 2000, 2001, et cetera. So you don't throw out any data, but you organize it into periods and look at all the data, like tide information, water levels, et cetera. Speaking of, so let me give an example here. So what you see on the screen are long-term average monthly water levels in lakes Huron and Michigan. They're actually basically the same water body from a water level perspective. But you see some years it's above, some years it's below in comparison to this long-term average that you see. And in Lake Huron and Michigan, there's maybe 5 or 6 or whatever gauges that they use to come up with that composite time series since World War I. And you see one of the gauges down here in this aerial photo. So that's one of the gauges that goes into this long-term time series. Well, there's a local gauge close by where you can actually get instant. So 3 minutes, every 3 minutes, it takes an observation. You download this. You see the websites there where you can download these things. At that, and so I only had the patience to download the last 3 years. And you see that here. So here's and it was this 3-year period right here. We're at a very high period in the record right now. This is well above the long-term average. But you see in red the 3-minute data, and then we kind of reduce the noise and things get smooth, reduced and get closer. So also from this local gauge, we have 60 years of hourly averages and daily averages. And see with the hourly in green and then the daily in black here, they get closer and closer and closer to that long-term composite average, as you'd expect. Now, if we were to count the number of hours that each of these water levels is exceeded, add them up, and then express it as 100% of the time values are at or above this value, we come up with what's called a flow duration curve. And so the long-term in blue, the long-term record is shown here 100% of the time. So there's the lowest monthly average right there, just below 176.5 meters. And there's the biggest value that was ever measured. And then we count all the hours and put them here. So 10% of the time, the monthly average was above 177. You get the idea. And so as you would expect, the local gauge, the long-term 60 years of record here in green and black kind of match that that characteristic signature, that duration curve there. Now, in the last 3 years, this red every 3-minute data, well, that's well above average, and that jumps out very clearly. Everything's above the average here most of the time. So there you go. This is what water quantity time series data looks like. You can have the actual measurements here, or the average values over some averaging period that I've shown in the legend there, or you can express it as flow duration curves. So let's talk about that. Oh, but before we do, let's talk about sediment, total suspended solids, TSS. One size. So as the bullet shows, TSS is not just one size, it's a bunch of sizes. So you can either define what D50, so the median particle size, or you can have a particle size distribution. That's what the PSD stands for. In any case, it's a bunch of particle sizes. And so in the world, according to NERP, this was a study 40 years ago, they were able to identify 6 different size fractions there, grouped by the amount of mass. So the smallest size fraction, 20% of the mass was in the smallest size fraction there. And it was, again, characterized by the mass fraction, but each of those has, you can attach a range of equivalent diameters, but more specifically, this settling velocity here. So the very fine particles, small particles, take a long time to settle out of the water column. Whereas the biggest, the 20% by mass, those biggest particles, with an average of about 100 microns, they settle out really quickly, 65 feet per hour type thing. Okay, so that's what total suspended solids look like. And you need to know this, and it's important to think in terms of describing sediment that way, because the small particles, there's a preferential settling of those. Sorry, the large particles, they settled out really quickly, as I showed here. And the smaller particles, they tend to wash right on through. And if you don't believe me, just watch. This is a photo out of my office a number of years ago, but you can see the heavy particles here settling out real quick. And then the smaller particles, they're moving right along and clogging up the pond downstream. Okay, so there's sediment, and you've got a model, EPA SWIM 5, that can handle that. So this example just shows one representative summer in a pond. It's for a pond design, and all of those 6 size fractions were modeled. I'm only showing 3 here. The smallest 20% of the mass, the largest 20% particles, the largest particles, 20% of the mass, and then the middlest size fraction there. You see the very fine particles, they stay in the water column a long time after it rains, and the concentrations of that sediment fraction are quite high compared to the large particles. They don't last very long after it rains, and the concentration is low. You can read all about this if you want to. Just go to that link there. And what you see is a picture of, wow, this was built 10 years ago. This is a picture of the biggest sediment loading event, and that's during construction. Okay, now if you're in a quandary about quantifying quantity and quality, maybe it's because we like to throw out special terms and terminology for these different plots and things. The rainfall hyetograph is the rain that kind of stimulates and stirs up things, creates the runoff. We call that a hydrograph, water quantity. Rainfall hyetograph, water quantity hydrograph. And then for pollutant concentration, we like to call that, many of us like to call that a pollutograph. But then the loading rate, the mass loading rate, so pounds per second or kilograms per second, we call that a lodograph. And that is you just multiply the flow rate times the concentration at the same time step, and that's your loading rate at that time. So flow hydrograph, there you go. Here's the flow. So cubic feet per second, let's say the area under that curve is the volume. Pollutograph, concentration, measured or computed in time. And then finally, when you multiply at each time step, you multiply the flow times the concentration, you get your loading rate at that time. And when you have that composite curve there, take the area under that. There's your total load in pounds or kilograms for whatever period that is. One event in this that's shown on the screen, or you can break it up by year if you have a really long term. So last year, I talked about hydrologic response units, and these are, my opinion, a very convenient way to take very specific surface cover types and attach hydraulic parameters to each of them. And we'll come back to that. Whether you're modeling or measuring things, lake levels or runoff results, you can look at statistics in any number of ways. So there's the basic stats up here, and then the percentile stats down here. For example, the 90 percentile water level in Lake Huron is about 580.6 feet. What that means is 90% of the values are 580.64 or less than. So this is value or less than type thing. That's what a percentile is. With the flow duration curves, like I just talked about, you can look at flow duration curves, depth duration curves, velocity duration curves. Now, you can count the number of hours and show that as a curve, or you can express it as probability of exceedance. And why we want to do that is because that lets us link together these two things. We can link these two statistical methods together with the duration curves together with this very simple equation. And so with the duration curve, 1% of the time, the depth value is whatever that says, 0.05 feet deep or greater. Now, do you see that? So the probability of exceedance is a value or greater. The percentile is a value or less than. So this is how they're linked. Percentile, this is in percentage, it's percentile equals 100% minus the probability of exceedance. So now we can relate these two things together. We'll come back to that. Okay, so these are what you see on the left there is what I just talked about, the typical water quality analyses or ways of modeling approaches, and then the quality parallel on the right. So this has a nice ring to it. A QRU, the quality response unit, is the same thing. We attach pollutant buildup and wash off parameters to very specific surface cover types. We can use the same statistics for both of them. And then I'm going to introduce two new types of curves. I talked about the flow, depth, and velocity duration curves. Well, now we have the pollutant concentration and the loading duration curves there. So same as with the HRU, the QRU, for the same, you can have the exact same land surface cover types or land use, whatever you want, and then attach the different water quality parameters to those. Run it through your model, and ideally you'd refine these, calibrate, if you will, these individual parameters so that when you run it for whatever that is, 25 years or so, and then you calculate the total loading per year, pounds per year, pounds per acre per year, or kilograms per hectare per year, you'll come up and try and match or compare that to the published literature values. So anyway, you take the flow, you can't see the green and yellow ones, but they're hidden behind the heavily impervious. But anyway, so it's much easier to look at the duration curves. There's your flow duration curve, your concentration duration curve. You multiply each of those together to get your loading duration curve, and then you take the area underneath, and there you go. There's your total mass load. So I'm not quite finished this yet. These are about 30 or 40% bigger than the literature values. But anyway, this is a proof of concept, and this is what I'm presenting to you in this short time. There's your proof of concept. Let's move on and look at two things: model results and measurements, okay? So the first one, we'll look at model results using that same QRU process. And this time we're looking at 21 years at a development site. And you can read more about this, go to this website here, look at the examples, and you can download the model and take a look at that. So, and then the next one is looking at not model results, but actual measurements. And you can go to the USGS website and you can find this data. There's a report that goes along with it. Now, do you see it says daily stream flow? I find I want higher resolution data. So 15-minute stream flow you can get. I don't like the daily. I like the 15-minute data set there. So you can go, oh, and this is the Atchafalaya River, by the way. There's the gauge number that you can go to the USGS National Water Information System, type in that number, and it'll bring you to this page eventually. And you can download the high resolution 50-minute data. Here's an aerial view of the river. Do you see that chocolate? It's like a river of chocolate. That color suggests that there's a lot of sediment in there. So let's take a look at that sediment data. And just for perspective, here's New Orleans, about an hour and a half to the east. Okay, so the first case study is a development site, small development site. Here's what it looks like a few years ago. So it's current hydrology, current hydraulic network. pre-development, we'll call that. Now, with that current hydraulic network, just a simple pipe to dump it into the bay, we're going to impose what I call an uncontrolled future hydrology condition. We're going to develop, we're going to put a big building, big ugly building there and some landscaping around it and dump it into the same network there. That's uncontrolled. You can't get a permit for it, but it's useful for comparison. And then there's the two controlled conditions where same proposed land use condition, but now we're going to polish it off in a dry pond in one case, a storage unit that's initially dry. The rain comes, the pollutants settle out, and everything that's treated there moves on. And that's the one that you can download the model. You can get the EPA Swim model for that at the website. Now I've added another, so I've increased the footprint and I filled it up with 4 feet of water. Okay, so now you've got more capacity to during quiescent times to settle out those particles. Give it that time it needs to settle out the particles. So you'd expect it would have better performance. Here's how we treat that in EPA Swim. So again, generate the loading, the buildup and the wash off of pollutants using that QRU approach I talked about. And then once it's in either the dry pond or the wet pond, we have treatment expressions that you can just type into EPA Swim there and it'll settle up. Now I'm only focusing on one here. I'm not listening to what I said earlier. So this example only targets that one narrow band right in the middle. And so I'm just looking at the settling velocity of 0.3 feet per hour. And that's how you type it in right there. Ideally, I should look at all mass fractions, model them individually, and then put them back together to find out the true average annual TSS pollutant removal. In any case, this is just to show you how this works. So we can run it for a long time, take a look at the basic stats, the peak flow and the total volume under those 4 conditions: pre-development, basically Mother Nature, undisturbed, lightly disturbed land, and then so these are all proposed conditions that isn't controlled. So it just dumps into a pipe, like I said, or the 2 pond options. And there's your peak flow statistics, and there's your peak concentration statistics, peak concentration, and then the total loading average per year right there. No, that's the total loading for that the total 21-year period. Okay, so those are basic stats. And then you can do your frequency analysis to attach return periods to each of those scenarios: pre-development, uncontrolled, etc. Same thing, you can attach return periods to each of those scenarios for the peak concentration of TSS. But what I really want to talk about is the flow duration curve. So here we go. If we look at the flows, and again, over a long period, it's hard to see visually what that represents. Much easier to see what's going on with the flow duration curve. This is Mother Nature right here. So the pre-development condition, this is the worst case, don't do anything, dump it in the bay type thing. And you see how both ponds, in terms of flow control, they both do roughly the same job. They're clawing back, they're getting closer to that lightly disturbed condition, but not quite there yet. By the way, we need green infrastructure or low impact development to get to this blue line eventually. Okay, but let's talk about water quality. So with the water quality, if we just look at the concentration, so that the concentrations aren't as attenuated with the dry pond as they are compared to the wet pond. So the wet pond attenuates those flashy or peaky total suspended solids concentrations very clearly right there. But then if we put it all together with this, what I call the lodograph, so again, multiply the flow times the concentration at every time step, put it all together, here's your characteristic curves. Both ponds do a good job. The wet pond, as you would expect, that reduces the total load quite a bit more than the dry pond. So that helps refine your best option in terms of treating long-term removal efficiency for TSS. There you go. Let's move on finally to the Chafalaya River. So this is the largest river swamp in North America, by the way, bigger than the Everglades, I understand. In any case, from that website that I mentioned, you can get 32 years. It's not, so these are grab samples, so it's not a regularly spaced interval, which is a bit frustrating because you have to actually create 15-minute or hourly to do the lodograph to get the flow times the concentration at each time step. In any case, there's 2 size fractions. Like I said, the the smaller fraction, less than 63 microns, and the all size fractions, the total suspended solids. And as you'd expect, the average concentration for that smaller fraction is lower than the average for all particles together. So 32 years measurements for both those fractions. This is what the concentration duration curve looks like, and you can come up with your statistics there. Now, as I mentioned, you need to put these in time, and like I said, forget about the daily stream flow. Let's go with the 15-minute stream flow data. I was able to get 6 years of 15-minute stream flow. So I took the stream flow and then I multiplied the concentrations times the flow rate here. Here's the flow for the last 6 years. The flow times the concentration, that's your loading hydrograph, and then create. Now I know what you're thinking at this point. This is analysis. We're verging on analysis paralysis, but let me get to right to the point because my time's up. With the flow duration curve, look at these percentiles. Let me just get to the bottom line here. When we look at these percentiles, and this last statistic is a measure of the ratio of the 90 percentile to the 10 percentile. If you look at that ratio and then compare that flow duration curve, those statistics, with the load duration curve, we're talking about two different shapes. And this is significant. Let me explain how. If you ever, I don't have time to talk about this, but hydromodification is a popular permitting process on the West Coast, California, and other states there, where you need to look at both flow and sediment delivery together concurrently. If you care about protecting the water course, you need to look at both of those things. If you just care about flood protection, well, you can tune out from this slide. Now, in that, here's an example of the types of criteria that they use. So this kind of tells you, this is for the regulatory requirements in this particular county, they tell you, you need to look at flows for the 10%, 30%, 50% of the 2-year return period, and then the upper bracket is the 10-year return period flow. I have no issues with the lower brackets here. I have a big issue with this upper bracket, the 10-year flow. Let me show you what that means. Okay, if we look at the flow hydrographs here on the top, the flow duration curve, you see the 1% probability of exceedance, 1%, that actually corresponds to the 10-year return period flow. Here, the 0.3, so these are right out of the regulations here. 0.3 is the value there, and then the 10-year return period flow is the upper bound. 30% of the 2-year flow, which happens to correspond to the 75%, so the 25 percentile or the 75 percent probability of exceedance. And here's the upper bracket. If you take those values and go down onto the lodograph, actually that 1% probability percentile, which corresponds to what's regulated, they're telling you need to go with the 10-year flow as your upper bracket. That upper bracket actually corresponds to only 30%, 38% of the TSS load, just because of the shape, the very unique shape of this lodograph. And then the lower bracket, which I have no issue with, that only gets 2% of the load. So that's a good lower bracket, but the upper bracket needs to be higher. So there you go. The current standard says thou shalt use 0.3, 30% of the 2-year return period, and then the upper bracket is the 10-year. Well, that only gets 36% of the TSS load. I'm not showing those lines on the plot here, but if you adjusted that to pick this as your upper bracket, somewhere up here, you'd get 90% of load. Enough of that. Let's wrap up. So future needs. Modelers, like me, we need to be more adventurous. We don't look beyond the basic stats and do the duration analyses and the percentiles. Regulatory standards, I think, could be a little more specific. For those that are fortunate enough to say something like percent of the time, 10% of the time, like this one here, more than 10%. So these are different standards for TSS, depending on what use of the water body is. We should be more specific and say the probability of exceedance or the percentile type thing. I think we can do better on that, and you know how to get those numbers from your measurements. Finally, I think the model developers need to be a bit more revealing, because EPA Icwmm doesn't produce the loading rate as a time series. So please, can we add that as a function to an upcoming release of EPA Icwmm so that we don't have to calculate it on our own? And that's all I have to say about that.